there, welcome to Completing the Square. So on here we're going to take a look at how to solve and rewrite quadratics in different kinds of forms. Luckily the first form you've already seen. So take a look at this first example and try on your own. All right, welcome back. So here we're going to take a look at the quadratic parent function, which you can see is already graphed on your paper. So we're going to look at a couple different key features. First of all, hopefully remembering what the quadratic parent function looks like. So I'm going to go ahead and reveal these answers first, and then we can talk about them. So hopefully you have y equals x squared, which is your quadratic parent function. Remember, domain is all of the values that I can put into the function. So all of my input, well, I can put a negative number in there. Yep, I can put 0, I can square fractions. And then the range, again, is the output. Well, if I square that number and I multiply it by itself, I'm only getting positive numbers. So you can see I wrote that in interval and in set notation. Increasing and decreasing. So this says where on the function are the y values increasing? Well, they're increasing when x is 0 to infinity. So that's that piece there in blue. And then where is the function decreasing? Well, that's on the other side, because we kind of read graphs the way that we read in English, left to right. Symmetry has y-axis symmetry. So if I fold it along the y-axis, I get the same picture. And then I also have a line of symmetry located at x equals 0. So here's what's also very nice. This right here, we've identified this before, but I'd love to talk about it again, is called the vertex of our quadratic. This one, it happens to be a minimum because it's a low point. And the good news is you can see that our line of symmetry goes right through that vertex. So that's one of the best things about it. We can also see that this graph is opening up. Well, instead of saying opening up, in math we say it's concave and we say up. So I'm going to draw it kind of like that, concave up. So vertex form is exactly what we're used to seeing. This is what we've been graphing for a very, very long time. So vertex form we've seen for quite a while. It looks kind of like this. You have a vertex, which is kind of what we graphed in red. So that's at H and K, but that's basically how the graph is moving left and right. We saw this during transformations. The A value is the one in the front. That's the one that we saw that if it's positive, it kind of did this. Remember, if it was reflected on the exterior, it was flipped on the x-axis. We also had some vertical stretching right here. We had some vertical compressing right there as well. Lots of different things. So how can we determine concavity? Well, hopefully that will depend on whether the A in front is positive or negative, because if it's positive, it's going to open up because it's happy. And if it's negative, that's what causes that flip for it to go down. Axis of symmetry, we can locate that by looking at our vertex. And you can kind of see that on our parent function. It goes right through that vertex. How do we know if it's a minimum or maximum? Well, that's going to depend if our graph is opened up or if it's opened down. So if I am concave up, well, then I'm going to have a minimum at the vertex. And likewise, if I'm concave down, well, in that case, I'm going to have a maximum. So all of that will depend on concavity. And then finding the y-intercept, we haven't done this one yet, but we're going to need it because we're going to plug in 0 because that's where it crosses the y-axis, and then we can find our y value. So y-intercept we're going to find here in a minute, because the first one, all we wanted to do is just locate the major aspects. So I'd love for you to pause the video and try this next example. You can see I've already provided a sketch. All right, welcome back. Hopefully this one went a little smooth because we've seen this before. Well, the graph went left 3 and I went down 6. So that's where I can see my nice little vertex. I can see 3 halves, so it's definitely going to stretch, but it's not flipped at all, which is really, really nice. I'm going to go ahead and reveal all of these answers so that you can check your work. So hopefully domain is still all real numbers. I can square any number. The range, I can see that it shifted down 6. So that's kind of where I can see that range. Increasing and decreasing. So it's increasing from 3 to infinity, decreasing from negative infinity up to 3. And I can see that line of symmetry is right there at x is equal to -3. The y-intercept, I'm sure you're wondering, where in the world did I get that? So here's where I work to show how I plugged in 0 and how I simplified it. You'll see that I left it as a fraction. This is crucial for upper level mathematics. We always will start leaving things as fractions. So the hard part is, what's going to happen when these quadratics aren't written in vertex form? How am I going to graph these in a really easy way? Well, there's a process for that. It's called completing the square. This allows us to rewrite a quadratic that's in standard form into vertex form. So standard form is kind of what this is right here. This is kind of what we're used to seeing. So there's some number plus bx plus c. This is actually how we've been used to seeing all of our quadratics. We factored ones like this before, but graphing them can be a little bit daunting. So first I want to show you, what does completing the square mean visually? So you can see I have some tiles over here, and what I'm going to do is I'm going to drag these over. So I need one x squared piece. I need 4 x pieces. So 1, 2, 3, 4, plus 4 of these pieces. So I'm going to try to literally build a square. If you've not seen these before, these are called algebra tiles. Think of them like area. So like x times x, that's where the x squared is coming in. And then same thing on the other one. So this is like a length of 1 and a length of 1. And then same thing. Here's 1 and x. So if it helps, that's kind of where those are coming from. Well, if I want to build a square, I could probably take these middle pieces and I can put 2 on this side and maybe 2 on this side. That's starting to look like a square, almost equal. And then, oh, look at that. These 4 can just squeeze in right to here. That looks like a square to me. So here's how we're going to write it. I can see that I already have x right here and x right here. And then I have a 1x, I have that, a 1x, and a 1x. So let's just rewrite this as x plus 2. So that's this one on the top. And then look at that. It's a square. I have another x plus 2 piece. Well, math people, we're pretty lazy. We like to write things together. So instead, x plus 2 squared. Well, that's a whole lot easier for me to graph because now I can see, okay, I've gone left 2. That's a whole lot easier for me to work with. These types of polynomials are called perfect square trinomials, and that's because we can rewrite them like this. The problem is not all quadratics look like that. So what we're going to try to do is actually create these perfect square trinomials. So let's try another one. All right, this one has the last blank missing. So I want to see if you can figure out how to make a perfect square trinomial. All right, you can see on this one, I've already got my little squares all nice and set up. So I have 1x squared. I have 6x pieces, that's the green piece, and I've left this part blank. Well, how am I going to complete this square? It looks definitely a little bit different because I've got an x right here and an x right here. This time I have 3 pieces and 3 pieces. So if I literally want to complete this square, I would need, I think you're starting to see where I'm going with this, 9 of those yellow pieces. That would complete my square. And then I would have x plus 3 squared. All done. On this one, hopefully what you did was 3 times 3. So that was 3 squared. Okay, interesting. All right, I want you to try this last one on your own and be careful, I threw a minus in there. All right, here's my algebra tile pieces. I have 1 x squared piece. I have -2, so I'm just going to add some negatives here. And then again, what can I use to literally complete this square? Oh, I just need 1 tile. And now I have matching pieces. So I have an x. This one's a little different because now it's -1. and then I still have that same. That's what I love about squares. Everything about them matches. So I have x minus 1 squared, and I'm going to put a positive 1 because that's what I used to complete this square. So you can kind of see on all of these different tiles that I've been using, every single time we basically took this piece, the B, and we split it in half because we put 1 on each side. And then in order to get to this piece in here, we squared that number. And that is literally what completed the square. That worked exactly like what we did up here. I took the 4, I split it in half, so I had 2 on each side. And then I squared that because here's 2 times 2. And that's where the 4 came from. So they all kind of follow that same exact pattern. So let's write these steps down so we can have them and access them for later. First thing you're going to do is get all your variables on one side. Anything with an x, put it on one side. And then we're going to take a look, and hopefully there's no ax squared piece. So what I mean by that is, do you have a 4x squared? Do you have a 5x squared? Is there something in the front? If so, we're going to have to deal with it. Then we're going to add something to both sides. And the thing that we added, remember we took that middle piece, we split it in half, and then we squared it. And that's what completed the square. All right, after that, we're going to go ahead and factor now that perfect square trinomial, and that's kind of where we used our tiles. And then if we're looking for vertex form, we're going to move it to one side. Step 5 is going to change a little bit depending on what exactly we're going to look for. So let's try to do one of these by completing the square, because somehow I have to try to graph that. And right now I don't know how because it's not in vertex form. It's just not very friendly. So let's complete the square. Well, my first step said I have to separate and isolate all my variables. All right, there's no ax squared, it's regular x squared. So now I can skip that other step. So now what I'm going to try to do is add something to complete the square. But if I add it to one side, well, math people are really picky about that because they say, well, then you have to add it to the other side, because I have to keep it nice and balanced. All right, so now we're going to take that B piece, split it in 2, like before, where we put them on the sides of our square, and square that number. And that's going to go up here. Well, that's positive 4. Oh, so I have to add 4 on the other side. Nice and balanced. Now we're going to factor this perfect square trinomial. You can do this with grouping. But if you're the visual person and you started to see those patterns, you can instantly factor these. They always factor the same way, which makes them pretty friendly. But the good thing is, once we split them in half, basically this was the number that we ended up using. So 4 over 2, and it matches right there. If you want to, you can always go back to our tiles and see that that's exactly how this worked. See how we split it in half? Here was the 2. See how we split it? Matched up there? Same exact thing. All of these are very, very similar. All right, and now I have this equal to y plus 11. Well, that's almost in vertex form. I just need to move everything back over. So now I have positive 2 right here, squared, negative 11. Okay, so now I basically rewrote this into vertex form. So now find all the key features. Here we have domain is all real numbers, range, negative 11 up to infinity. You can always do a sketch if you'd like to see these in action. Increasing from negative 2 to infinity, decreasing on the other side. And then you have the line of symmetry and the y-intercept. And here's how I found that y-intercept. So hopefully all your answers look something kind of like that. Again, if you'd like to do a sketch, you can always do that. I recommend a sketch if you're somebody that likes them, just because I think it makes them a little bit nicer. So here's that line of symmetry so you can see exactly where I got that from. Okay, well, this one has a lot to it. So first thing I'm going to do is hopefully move that 6 over. So I'm going to subtract the 6. Ooh, I do have a 3x squared, so I do need to factor out that 3 from both sides. Okay, now I'm going to try to complete the square, make it a perfect square trinomial. So that means I need to add a blank on both sides, because again, if I add it to one side, I have to do it to the other. So we've got to figure out what's going to go in that blank. So I'm going to take 16 divided by 2 is 8. 8 squared, so I'm going to add 64. But before you add 64, 3 times 64. So 192 goes on that side. That is always the trickiest part when we factor out the A's. All right, simplify everything up. Make sure you factor that perfect square trinomial. But again, we can always use that shortcut if that helps. So, what multiplies to 64 adds to 16? Oh, well, that's just 8. Oh, look at that. There's the 8. There's the 8. So you can kind of start seeing where all of these are coming into play. Just be sure you go ahead and move that 180 to the other side. So it looks kind of like that. All right, so I'm going to go ahead and have my sketch. So I went down 180, I went left 8. I did stretch, but I didn't flip. So hopefully here you have domain, all real numbers, range, -180, up to infinity, increasing from -8 to infinity, decreasing on the other side, line of symmetry right there through x equals -8, and my y-intercept at 12. Again, I'm going to show you where I got my 12 from. I always like to plug it into the original. I think it works a little nicer, but it's completely up to you how you'd like to plug in. So solving, the steps are going to work identical. So what do I need to move first? Okay, got to isolate everything. So I'm going to move the 12. Well, there's no a next to the x squared, so that's going to make my life a little bit easier. So I'm going to jump straight to completing the square. Add to something to both sides, leave it a blank. All right, so I'm going to take whatever's in the middle. Remember how we split it in half to build our square? Square it, goes over here. So I've got 16 and 16. Nice and balanced, because I'm not changing anything. I'm just doing a rewrite. All right, perfect square trinomial. Well, again, you can always pause and say, what gets me to 16 and adds to 8? Oh, well, that's pretty friendly. 4 and 4. So if that's easier, you can always factor by grouping, and you're going to get the exact same answer. All right, I got -12 plus 16, giving me 4, but I'm solving. Ooh, how can I solve for oh, I see a square. So I'm going to undo that. So now I just have x plus 4. Well, that's pretty friendly. Here's the tricky thing. Technically, 2 squared gets me 4, so it could be 2, but -2 squared also gets me to 4, so could be -2 as well. So just be real careful when you solve these, because you do have 2 possibilities. With 2 possible solutions, x could be -2 or x could be -6. Here's the thing. This took a lot of work, but it was friendly. What if you tried to factor from the very beginning before completing the square? Well, what would multiply to 12 and add to 8? 6 and 2. I feel like I've seen those numbers before, because if I try to factor, oh, well, look at that. I get the exact same answers. So let's take a look at, well, why would I want to complete the square then? So let's take a look at this example here on the left. Okay, I'm going to try to solve. So I'm going to try to do this with completing the square. So I'm going to go ahead and move a couple pieces over. Oh, I see those are all kind of evenly by 2. So why don't I just divide everything by 2 to clean it up? I can do that. So now it starts to look like that. All right, well, I'm going to take that middle piece, divide it by 2, and square it. Okay, so I'm going to add 9 to both sides. Perfect square trinomial, which it worked out really nicely. I squared rooted both sides, positive and minus, and then I have 2 solutions. So here's the thing. This one would not have factored. So if you try to factor 2 times 8, okay, what gets me to 16 and adds to negative 12? Ooh, nothing would have worked here. Factoring doesn't always work. Complete the square does always work. So it does have a certain advantage. All right, so hopefully on this one, you already moved the 10 over. Ooh, that last one I could divide by 2. This one I can't really divide everything by 3 because that's not going to be pretty. So this time, let's just take a 3 out. So I now have regular x squared minus 2x. Here you can see I took the middle part, split it in half, and squared it. Ooh, see how I did 3 times 1? Okay, well that cleaned up a little bit nicer. Now I can divide both sides by 3. Now I can square root both sides. Just be sure you have the positive and the minus. Plus or minus, they always come in pairs. And then I split my answer into 2 different solutions. All right, last one. Woohoo! There's no A and everything's been isolated. So let's jump right into completing the square. So I don't have to move anything. I can just jump into adding something to both sides. So I've got positive 1 plus a blankety blank blank blank. This one's a little odd, isn't it? Well, the B is 1. That's odd. So I'm going to have 1 over 2, or 1/2, squared. So that's 1 over 4. So I think now you're starting to see where completing the square, it's a great method. It just might get messy. Okay, so let's try to simplify this perfect square trinomial. So that's going to be plus 1/2 squared. Now I need to somehow simplify this side. So I'm going to rewrite this as 4 over 4. That's the same thing as 1 plus 1 over 4. Okay, so now I have 5 over 4. Okay, that looks a little bit nicer. Do what we do best. Square root both sides. Positive or minus, plus or minus. Never forget that plus or minus. All right, so I have x plus 1/2 left here. And I've got plus or minus. Well, root 5 isn't really friendly, so I'm going to leave it as root 5. But square root of 4 is nice. So I'm going to make that a 2. Last thing, just be sure to subtract the 1/2 from both sides. So those are going to go away. So I have one possibility is going to be root 5 over 2 minus 1/2. So you can leave it like that. If you would like to shrink that up a little more, you could. So anything in red. And then the last one, which will be negative root 5 over 2 minus 1/2. Or again, if you'd like to combine those up, root 5 minus 1 all over 2. Either of those in red, I will take.